Calc 2, section 5.3, the definite integral. This is going to have some definitions, but it won't be as long as that last section 5.2 video. But it's important here to understand as we go, so read it slowly and carefully. We're going to let f of x be a function. Be a function defined on a closed interval a to b, and closed interval you write with these square brackets, period. We say that a number I which I guess we should say is an element of the reals, is the definite integral of f over the closed interval from a to b. I guess we should put comma here. And that capital I is the limit of the Riemann sums that's the summation k going from 1 to n of f of c sub k times delta x sub k. If given, and this may sound familiar from differential calculus, given any epsilon greater than 0, there exists a delta greater than 0 such that for all partitions, this is the upside down A, for all partitions P, which is just a list of x coordinates, of that closed interval from A to B, with this double strike, P double strike, looks like an absolute value and an absolute value, is less than delta, and any choice, C sub k in that interval from A to B, we have, I've got to go to the next screen, but let me hold off on that so we can look at this a little more slowly. I should have written smaller, but there's still more to go. So the definite integral, that's what we're trying to define. And really what this is saying is the definite integral is this real number I. It's just a number. The definite integral is just a number. And it's because we're looking at this as just a number that it becomes sort of impressive later on that we look at the integral in a different way, and it can be viewed in many different ways that can be very helpful. But this one, the definite integral, is just some number I. F is a function defined on the closed interval from A to B. So there can be, got to be defined on the whole interval. We say that a number I, which is just a real number, is the definite integral of f over A to B, that closed interval. And I is the limit of the Riemann sums this sum, if we take the limit as the norm, this norm of the partition goes to 0, the limit of this product, it's the same as that I. If given any epsilon greater than 0, there exists a delta greater than 0 such that for all the partitions and any C. So if you've written all that down, this leads to the nice part. The absolute value of the summation k going from 1 to n of this f of c sub k times the delta x sub k, that number that you get minus the I, the definite integral, is less than epsilon. So in other words, the difference between the actual integral here and the summation, which is a finite sum, is really small. We write this I, which is the same as that limit as the norm of the partition P goes to 0 of the summation, same old summation, k equals 1 to n of f of c sub k times delta x sub k. We're going to write that differently as the integral from a to b, because this is on that closed interval, of f of x dx. Now we're going to learn how to calculate this as we go, but let me change colors here just so I can make it a little nicer. This is the integral sign. This is the lower limit. It's the same as this lower limit in a sense. Well, it's really from that interval from a to b. The left-hand side of that closed interval. B is called the upper limit. F of x, like the dividend in division, this is the integrand. And dx is special. It can be thought of in very different ways. But this is the variable of integration. And the whole thing all together is the definite integral of f from a to b. Okay. These Riemann sums, the limit converges to I. F is called then integrable if this integral can be found at every x, because x is an element of that closed interval. So, does that make? This is just notation right now. We don't know how to do it yet, really. You might know some of it, but we haven't talked about it yet. Okay, next screen, there's a Theorem 1. And it is the existence of the definite integral. Now you might say, why would you have to know that it exists? Well, little bit important because you may want to just stop before you start trying to work something. This is if you've got a continuous function. If f is a continuous function. On that closed interval from a to b, comma, then its definite integral over the closed interval from a to b exists. So, you know that for continuous functions, if they're continuous on that interval, you've got a definite integral. You don't have to worry about finding one or that if it exists or not. It does exist. So what does this mean? Maybe, let's see, a Riemann sum associated with this particular is less than the upper sum and greater than the lower sum. The upper and lower sums converge to the same value when the norm approaches 0. Therefore, all these Riemann sums, it's sort of like the sandwich theorem. If you remember the sandwich theorem, I think you did that in CalcII, where you sandwich things together. If we know this upper sum is too big and the lower sum is too small, but if we go to infinity, and if we know that, I guess, the Riemann sum is between, but the lower sum as you go to infinity converges to the same value that the upper sum converges to, and if this one's got to be in between, then this one converges to that same one. They all converge to that same I. So this is very helpful. We know that all these are nice numbers. Another way of talking about Theorem 1, it says, if the function is continuous over a closed interval, then it is integrable. If it is not continuous, you don't know. It may or may not be integrable. An example of something that is not integrable, let me get that. If you have a piecewise function, say f of x equals 1 if x is an element of the rational numbers, and it's 0 if x is an element of the irrational numbers. So if you're looking at a function, and here's your x and here's your y, and you go along and you say, okay, 0 is a rational number, so it should be 1. Even 1 is a rational number, so it should be 1. I'm sorry, I put a dot down here. It should be up here. 2 is a rational number. It'll be 1. 1/2 is a rational number. It's 1. 1.5 is a rational number. It's 1. But what is the square root of 2? See, the square root of 2 is like 1.7 or something. So it's someplace over here, and it is 0. What is the square root of 1/2 and things like that? Any of those crazy square roots, you're going to have dots down here on the x-axis because it's 0. And what I hope you see is this thing is not continuous, and it just bounces around way too much. In fact, between any two numbers, real numbers, if you'd like to put that in there, is a rational and irrational number. You can find one. So, it doesn't matter whether you pick two rationals, there's still an irrational between it. Every number, this is going to bounce up and down all the time. So if you think of using a Riemann sum, which uses the biggest interval for any of your partitions, the tallest part, because between any two numbers is going to be a 1, because there'll be a rational number. The upper sum will always be 1s up here, and so you're going to get from 0 to 1, say, you're going to get 1, because 1 times 1. But if you choose the lower sum, the LRAM, in a sense the lower sum, then you're going to have to choose the Q prime, an irrational number, and everything will be down here on the x-axis, and it'll just be 0. Since those two do not approach the same number, we don't have a nice definite integral. We can't find the integral over any interval here, closed, so it is not integrable. There are some properties of integration of these definite integrals. Oops. I'm getting a little sloppy in my writing. So let me see if I can slow down. The definite integral from a to b of some function f of x equals the opposite of the integral from b to a of that function of f of x. I forgot the dx. Should be a dx here. So in other words, if you switch the limits of integration, you've got to change the sign from positive to negative, from negative to positive. Second, take the integral from a to a of some function f of x dx. You get 0. Because it's just 1 point for this function, doesn't really matter the function, you get an f of x, this height, but you have no width. So you get 0 times whatever, and it's 0. So how about the third one? The integral of from a to b of some constant k times a function f of x dx. You can pull that constant out, just like you can for the summation, from a to b, and just worry about the function f of x. It'll make it easy, a little easier. IV, the fourth one. The integral from a to b of f of x plus g of x dx. Notice I put parentheses around both of those. You can split that up just like you can the summation. The integral from a to b of f of x dx plus the integral from a to b of g of x dx. And this works for subtraction also, but not multiplication division. Something different there. Rule 5. The integral from a to b of f of x dx plus the integral from b to c, a to b, b to c, of f of x dx. These functions are the same. You can put that together and just do the integral, skip the b, go from a to c of f of x dx. Those are the first 5. There's a couple more, so you might want to write these down. Number 6. The minimum value of f times the interval from, I guess the length of this interval b minus a, is less than or equal to the integral from a to b of f of x dx, which is less than or equal to the maximum of f times the length of that interval from b to a. Now this should make sense, I guess, if you think about it. Suppose you've got a function f that does something like this. That's the function f. The minimum value is this one down here. So that's the minimum. You go from this a to this b, say, and you have a maximum up here. And this is if they have them. If they don't have a min or max, this doesn't work. But the area under the curve would be this area down here. Well, this minimum height times the b minus a is just this rectangle down below. That is less than the area I just shaded in before, which is the area I just shaded in for the function is less than this big rectangle because of that maximum height here. Sort of a logical, if you draw a picture you can see it. And number 7, if the function f of x is greater than or equal to g of x on some interval from a to b, closed interval, that implies that the integral from a to b of f of x dx is less than or is greater than or equal to, not less than or equal to, the integral from a to b of g of x dx. Makes sense. If this function f is above the function g, then the area under the curve has got to be greater. Special case that you might talk about here is when g of x is equal to 0. You might use that more often than others, because then you just want to say if the function is greater than 0 on this interval, then its area is greater than 0. Might be useful. So we would like to, I guess, come up with what they're going to call a precise notion of an area of a region. And we need a definition. If y equals f of x is greater than or equal to 0 on some open interval from a to b, then the area under the curve and really above the x-axis, that curve y equals f of x, over a to b, is this definite integral. The area equals the integral from a to b f of x dx. It might sound like we're saying the same thing again, but this is important. If your function is above the x-axis, is what it's saying, then that definite integral is the area. What we'll find out later is if the function goes below the x-axis, it will count anything above the x-axis as positive, but it'll count anything below the x-axis as negative. So when you find the definite integral for this, from this a to this b, you've got a positive, and then you've got a negative, and then you've got a positive. It doesn't really give you the area under the curve or between the curve and the x-axis, because this area is negative. If it's always positive, if that function is always positive, then it will. So you might have to divide things up. Find the area from this a to whatever, and then take the opposite sign of this area, and then add the next. So they're just trying to make sure that you understand this precise. In other words, let's take a function y equals 2x, and on this interval from 0 to 1. First of all, it could be useful to graph this. Let's see, from 0 to 1, and at 0 it is 0, and at 1 it is 2, just a straight line. So this area, if you think about that, the area of a triangle is 1/2 the base times the height, which is 1/2 the base is 1, the height is 2, but those cancel and just give you 1. Okay. If you want to find the integral from 0 to 1 of this function 2x dx, first of all, you find the antiderivative of 2x. That is 2x squared. You add 1 to the exponent, divide by the new exponent. And you evaluate that from 0 to 1. So these 2's are going to cancel. It's really x squared. So you plug in the top value, 1 squared, and subtract, plug in the bottom value, 0 squared, and you get still 1. We should probably talk about the average value of a function. Remember, the average value of a function is when you take some function and you find a y value from this a to b stuff that this area of the rectangle, which is that average value, times the b minus a is going to equal the area under the curve from a to b. That's the average value of the function. This works whether it's above or not. So what is the formula? They use AV and then in parentheses f. Average value of the function is 1 over b minus a, because you take the area underneath the curve, divide by the b minus a, and you'll get this height. So the area from a to b of f of x dx. For example, number 60, page 278. F of t squared minus t on a negative 2 to 1. We want to find the average value of the function, the AV of f. Well, you need the integral, 1 over b minus a. Let's see, this is the a and the b right here. So it's 1 minus a negative 2 from, a negative 2 to 1. The function is t squared minus t. Put that in parentheses, dt. Well, let's see. This is really 1 over 3. And the t squared minus t is really the integral from a negative 2 to 1 of t squared dt minus the integral from a negative 2 to 1 of t dt. Remember, this is multiplying everything. This is 1/3 times, well, this is t cubed over 3 from a negative 2 to 1 minus t squared over 2 from a negative 2 to 1. I'm going to have to squeeze this in a little bit. So it's 1/3 times, this is 1/3 minus 8/3. Minus 1/2, and then with the negative 2, it's still going to be minus 1/2. I'm sorry, 2 squared, 4/2. Oh gosh, it's getting too messed up. Okay. So let's write that on the next screen. Okay, let's try that again. So this is 1/3 times. Now, if you'll remember, you plug in the 1 minus plug in the negative 2. So plug in the 1 cubed over 3, minus plug in the negative 2 cubed over 3, minus, better be careful here, plug in the 1 squared over 2, minus plug in the 2, negative 2 squared over 2. Okay. 1/3 times. This is 1/3 minus a negative 8, so it'd be a positive 8/3. Right? Minus, this is going to be 1/2, and then this is minus, but it makes it a plus, 4/2. So this is 1/3. This becomes 9/3 or 3, and this is 3/2 positive. So we multiply by 1/3. We get 1 plus 1/2 is equal to 3/2. All that work. That is the average value of the function. Remember how to check these. The check is calculator. Let's look at y equals. Let's clear that out. Maybe that was correct. This starts out with the t squared minus t, or we'd have to use x squared minus x. The window, if we do a zoom standard, let's do a zoom standard. Get that nice picture. We can then do this from a negative 2 to 1. And do a zoom fit. And so it looks a little bit, so it's going to be a little bit underneath there. We found the average value to be 3/2 or 1.5. So if you take this and take the area of this interval, this is 1, 2, 3 times the 3/2, you get 9/2 or 4.5. If if we find the area under the curve from -2 to 1. How do you do that? You go second trace to get to the calc menu, number 7. The lower limit is, and make sure you're in function 1 here, y1. -2 is the lower limit. 1 is the upper limit. And it is 4.5. The area under that horizontal line at 3/2 is 4.5. It's the same thing. Okay. Some more examples. Wow. I've done it again. Number 6. This is in the assignments. It says, let's see, given the limit as the norm of the partition P goes to 0 of the summation k going from 1 to n of the square root of 4 minus c sub k squared times delta x sub k. P is on the closed interval from 0 to 1. And they want us to express the limit as a definite integral. So how do you do that? Well, first we change the color so we can mark things a little bit. So we need a definite integral. We need the integration sign. We need the limits. These are the limits, a to b. So this is going to be from 0 to 1. We need the function. Well, this is our function right here when we put an x in there. So this is the square root of 4 minus x squared dx instead of delta x. And that would be the definite integral. Now I'd say we should go ahead and find this, but we haven't learned how to do this type of integration yet. That's number 6. Another example, number 10. Suppose f and h are integrable and the integral from 1 to 9 of f of x dx equals 1. The integral from 7 to 9 of f of x dx is, let's see, a 5. And the integral from 7 to 9 of h of x dx is 4. So, we're supposed to use the rules of integration to find the integral from 1 to 9 of a -2 times f of x dx. Well, because there's a bunch of parts to this, you're not going to have any trouble showing 4 steps, but you'd like to make sure when you look back at this that you know what you did. So the first thing I'm going to show is that I pulled out that constant, because you can pull out a constant. Now you get the integral from 1 to 9 of f of x dx, and that has a value. This one right over here, it is 1. So this is really just a -2 times 1 or negative 2. We're going to just do one more from this, but these are the ideas. What is the integral from 7 to 9 of f of x plus h of x dx? Well, this comes from the integral 7 to 9 of f of x dx plus the integral of 7 to 9 of h of x dx. Now this integral is 5. This integral is 4. So you get 9. And they've got a bunch of those parts that you can show that you remember all the rules. One more, and then we'll call it quits, and you can start working on yours. Number 20. The integral from a negative 1 to 1 of 1 minus the absolute value of x dx. You want to graph and find the area. So what they're having you do here is show you that there's other ways of doing some of this stuff. From a negative 1 to 1, not very straight lines, but call this a negative 1, call this a positive 1, and this positive 1 on the y-axis. This function, 1 minus absolute value of x, you can graph it a bunch of different ways, but let's plot a few points. If we put it in a negative 1, absolute value says it's a positive 1, 1 minus 1 is 0. Put in a positive 1, absolute value is positive 1, 1 minus 1 is 0. Put in a 0, the absolute value is 0, 0, and you get 1. Now you might say we just connect those, and that should work. Just to check, put in a negative 1/2, it would be a positive 1/2. 1 minus 1/2 is a positive 1/2, and yes, you get this. Get the same thing if you do it on the other side. So you get this triangle. How do you find the area of a triangle? It's 1/2 the base times the height. The base is 2. The height is 1. So these are really hard multiplications. 1 times 1 is 1. But make sure you draw a picture, show some steps. You've got your 4 steps there. I hope this makes sense. If you have other questions, make sure you send me an email and I'll get back to you. But go ahead and start working. Section 5.3, Calc 2.